Dear ladies and gentlemen, I'm very happy to welcome you here today to our EMAG webinar, High Efficient Grinding System for Shafts. Today we want to show you different solutions for grinding of shafts. But before we do that, I want to give you an organizational remark. If you do have questions, just post them into our chat, and then it will appear here on my monitor and we will try to answer them right away. If we can't answer every question due to time reasons, we will come back to you after the webinar to leave no questions open. As I said, today we want to focus on high efficiency grinding system for shafts. My name is Tobias Rötlingshofer. I'm in the grinding technology department at EMAG, and together with me here in the studio for the webinar today is Manfred Winkler of our technical sales department. So, high efficiency grinding system for shafts, what do we want to show today? We will begin with the overview of our high production grinding systems for the shafts, and then we will see them on different applications. For example, rotor pieces, at first the electric rotor shaft, then the CV joint, and we will conclude the webinar with the CVT shaft. But now for the grinding system of EMAG, Manfred, what can our audience expect today?
Yes, so first, also from my side, welcome to this webinar, and thanks for your interest on the EMAG grinding systems and grinding solutions. Let me give you first an overview for the EMAG grinding systems. The know-how of the different grinding technologies which are bundled in the EMAG Group include the non-round grinding of company KOP, the combination technology hard turning and grinding of Reinecker, the universal grinding of Weiss, the OD grinding of Carstens, the gear grinding of Simultaneous, and also the crankshaft grinding of the Naxos Union. So you see, basically we can offer you a solution for almost all your grinding tasks in both fields, in the production and in the universal grinding area. Today we are focused on the production grinding machine, and EMAG has two types of production grinding machine. One are the horizontal and the second are the vertical production grinding machine. First, I want to give you an overview about the horizontal production grinding machines type HG2. All these grinding machines are designed with a cross slide. This means the grinding wheel make the infeed and the cross movement. For this, all different machine variants which you can see here, we have standard components like workhead, tailstock, steady rest to support long shafts, also in-process diameter measuring units and axial measuring probes. We have different dressing units to dress corundum grinding wheels and CBN grinding wheels. And also this machine are able to grind with oil or with emulsion as coolant, and also different automation systems for automatic loading and unloading are available. Now let's have a more detailed look on these different types on the HG2. On the left side, you see this machine type HG2. You can get only with one grinding spindle, and this grinding spindle is equipped with a corundum grinding wheel. You can make a straight plunge or an incline plunge grinding, and the maximum length is up to 400 millimeter. The next is the HG204. This machine can be equipped up to 3 grinding spindle. Therefore, the machine must be equipped with a B-axis, and this B-axis brings the second or the third grinding wheel in the grinding position. This machine we offer with CBN and corundum technology, and this machine is also up to a length of 400 millimeter. The HG208 machine, the next one, is basically has the same features like the HG204, but this machine you can use for shafts up to a length of 800 millimeter. The next, the HG208 double wheel machine has a special design. On this machine we have two cross slides, and on these two cross slides we have placed on each cross slide a grinding wheel, and on this icon you can see we can grind simultaneously with these two grinding wheels on the shaft. This comes to a much shorter cycle time if you use only one wheel. Also on this machine we offer CBN technology and corundum technology. The last, on the right side machine type, you can see HG208 center drive. The center drive has a special design. The difference is the workpiece is not clamped between centers. On the left side the workhead and on the right side the tailstock. This shaft is driven by a center drive unit in the middle of the shaft, and therefore the ends of the shaft, the right side and the left side, is open to grind OD or grind ID. Now we are coming to our vertical production grinding machines. Here we have two types. On the left side you see the VTC 315 DS. This is for shafts up to 700 millimeter. And on the right side you see our VTC 100. This is for shafts up to 400 millimeter lengths. So on these vertical machines there is something special. You can get these machines one side with a turret on the left side and a grinding wheel on the right side. This you can see on the icon on the left side. This is a combination technology. The turret is not only used for the turning of diameters and faces, it's also used for loading, unloading the parts. On the bigger machine, on the VTC 315 DS, we offer only CBN technology for grinding. On the smaller machine, VTC 100 GT, you can find also CBN and corundum technology. And if the machine is equipped with two grinding spindles, then we can have simultaneously grinding, and this come to a much lower cycle time. It's different like if you grind only with one. So if you have a higher production volume, we are using always the concept with two grinding wheels.
Just one moment, Manfred. We just got the first question here out of the audience to our grinding systems. The question is EMAG capable of grinding shafts longer than 800 millimeter?
Sure. It's possible to have longer shafts like 800 millimeter. Today we focus on the production grinding machine of our size 2. We have also production grinding machines size 3. And on this machine we can grind the shafts up to a length of 2 meters. So now let's have an overview about the workpiece which we focus on our shaft grinding machine. You see gear shafts, you see rotor shafts, you see CVT shafts, you see CV joints, steering shafts. So basically we concentrate on each type of shaft which from the quality request on the drawing a grinding process is necessary. Today we select these 3 parts to show you later some interesting applications. These are the rotor shaft, the CVT gear shaft, and the CV joint. Why we select these 3 parts? Worldwide we are discussing now, we have a big problem. It's climate change. We have to reduce the CO2 emission dramatically, and therefore the European Union intends that they don't longer allow the registration of cars with combustion engines after 2035. And this intention you can see also on these diagrams. You can see the expected global sales of cars in the next 10 years. These diagrams are from the well-known management consulting companies A.T. Kearney and BCG. That's the Boston Consulting Group. On the vertical axis, you can see the millions of cars which are sold, and on the horizontal, you can see the timeline for the next 10 years. And it's very clear, the blue one, you can see, these are the cars with a combustion engine, and this will be decreased in the next 10 years. And the cars with a hybrid drive or with a battery is increased. The hybrid, you can see it's the gray columns, and the battery are the orange columns. And these three parts which we are talking now and show you applications, this will be in a high volume in the next 10 years in the hybrid, in the battery, and also in the combustion cars. So the first part which we show you different and is interesting application will be the electric rotor shaft. And Tobias, you will show us all these different applications.
Yes. Now, first workpiece, the electric rotor shaft, which is the core in the end of our electric motor. How does it look like? At first, I want to give you a short insight into such an electric motor. For example, you see here the electrical part in the end. In the middle, you do see the electric rotor shaft itself that is posed inside the static of the electric motor. So the rotor does rotate then, and the rotation goes via a gear train compiling of something about 4 gears to our tires. Now we do take this electric rotor shaft, take it out of the motor and show it here. Here it does still have its laminated core, which gives the rotor shaft its electrical capabilities. But you can already see here, we do need to have mechanical elements like bearing seats. And if we now strip down this laminated core of the rotor shaft, we come down to this drawing. That is an example how such a rotor shaft can look like. And I will now go through the features of such a rotor shaft and the manufacturing challenges for these features. At the beginning, we start on the right side with a bearing seat and the tolerance grade about IT6, a roughness about RZ4 microns, and a roundness around 3 microns that we need here for our bearings. Corresponding to this bearing seat, we do have a shoulder with a running feature here in order that the bearing can be put against this shoulder. After the bearing seat, the rotor diameter comes, where we could put on the laminated core for the electric capabilities. And in order to put this on, we do need here again running capabilities. We do need the concentricity, and we do need a certain roughness that we can slip this core on this rotor, and then later on for the high rotations that such an electric motor has to ensure the correct function of the complete setup. Then some of those rotors are equipped with a transverse groove that limits the laminated core for rotational movement, and that helps slipping it on the rotor shaft. So now after this rotor diameter, we do have at the end again a bearing seat with a shoulder and a locking groove that we can use a locking device that the bearing does not slip off our rotor shaft while the rotor shaft rotates. And now we are leaving the electrical part, because in the electrical part we don't need to have lubrication, we don't want it in here, but we come to the output where normally a gearing, as shown on the slide before, is imposed. So here we do need lubrication. And in order to separate these areas on the rotor shaft, we do have a sealing seat, which normally has to be twist-free and has to have a roughness between RZ1 and 3 microns. And so after this sealing seat, we can then have the output gear that can be internally, externally geared. It can be just that a gear is to be slipped on the rotary shaft. That is just up to the designer who designs this rotor shaft, what he intends here for the output. But we want to focus on the manufacturing of the features just shown. How can we get them ready? One precondition could be that the shoulders are allowed to be turned, which is quite some often the case. And if you then have the need to have the same, not exactly the same, but similar rotors on the same machine with somewhat lower batch sizes, you need a more flexible solution with turning inside, and that is why we show you here our VTC 100 GT machine in the combination equipment. So we do have here a turret on the machine and a grinding spindle, and that gives us the possibility to machine the rotor as shown on the left side of the slide. At first we begin with turning the shoulders and turning the locking groove, because of course after we have measured the actual positioning in order to get the right position, for example, for the locking groove. Then we can either finish turn the diameters that just are turned and pre-turn the diameters to be ground in order to reduce the grinding allowance on this rotor shaft. After these turning processes, we get to the grinding processes. Now there is one thing we have to note, that the width of our grinding wheel is somewhat limited out of the geometry of the rotor shaft combined with the inside geometry of our machine. As you can see here on the downside, we can't have just a very, very big grinding wheel. We need to keep it smaller in order to get in there for the last diameter. And that is why we do not plunge grind the seats. Therefore the grinding wheel is big enough. But for the rotor diameter, now we do have to skive grind it. We just do have to take an actual movement around this rotor, along this rotor shaft, in order to grind it to its finished quality. And in order to be capable to do this, we do have also here the pre-turning to reduce the allowance to a minimum stock. Now I just want to go to a question that was posted here in the chat, because it fits very well to this part. It's the question, are the rotor shafts hardened or soft? I just can say we have seen all different possibilities here. We have seen complete hardened rotor shafts. We have seen complete soft rotor shafts that then could be probably also just completely turned. And we have seen also rotor shafts that are both, that are for the seats are hardened and for the rotor diameter, for example, soft. So again, here it is the designer and what he intends for the mounting and for the use of this rotor shaft, what he needs. Now back to our example. For the VTC 100 GT is now here equipped with the turning tools on the turret. On the turret is also an in-process measuring head for the grinding, the axial alignment unit, and a workpiece change gripper. With such a setup, we can get to a cycle time about 170 seconds, which will come just with a shift model of the customer. It can come up to 100,000 parts per year in a tolerance about IT6 and a roughness of about RZ max 5 micron. Now I want to show you in a video how this is really transferred to practice. At first, you do see the workpiece is put on the internal gearing on the automation to align it, and then it has to be turned, because in the machine we want to grip it from above inside this internal gearing. Then the actual alignment takes place for the correct actual machining of the, for example, the locking groove that is done here. And then on the downside, we begin with the turning of the shoulders. And here of a hardened part of such a rotary shaft, and then the diameters of the seats. And then the soft rotor diameter is here turned with a different turning tool, of course, and made fit for the skiving grinding. After this turning process, we do come to the turning process of the upper side of our rotary shaft. Again, the shoulders are machined, and then the diameters are turned either to their final quality or pre-turned for a grinding operation, which takes place after our turning operations. Here now the grinding is done with an in-process measuring head, as you can see. And after this seat, the skiving grinding of our rotor diameter is done. You see the actual movement of the grinding spindle along the rotor shaft. And to conclude the workpiece now, the seats on the downside are ground to their final quality. And after this grinding process, the rotor shaft is finished in this machine and can be taken out to our automation again. So you did see here a possibility to manufacture such a rotor shaft in a combination machining. Now, what happens if the shoulders are not allowed to be turned but have to be ground? Then we can come also to a flexible grinding horizontal possibility on our HG208 with an B-axis in order to realize, in this example, 3 different grinding operations. At first, one side of the shoulders are plunge ground with an angular set grinding wheel in order to grind not only the diameter but also the shoulder. In the second step, also a plunge cut with an angle. Our rotor diameter is ground to quality. Those diameters are ground with different wheels. For one reason is that in the middle of this rotor shaft, we do have such a transverse groove that we did introduce at the beginning. And now, at least at the finished grinding process, we have to separate those two elements in order not to see this transverse groove then also on our seats, because this groove will come to a change in the grinding forces while machining, and then there could be just the groove be seen also on our seat. The third grinding operation now is the seats on the second side with the left-hand shoulder then, and therefore the angle needs to be put in the other direction than for our right-handed shoulders. So we have here a machine now with 3 grinding units with 3 times vitrified CBN wheels for the grinding. We do come down to a cycle time of 115 seconds, which will come up to about 150 parts per year in the same tolerance classes than the example before. If we now want to get more productive, we do need to get machining operations done simultaneously. That is what we will show here on this vertical machine on our VTC 315DS. Here it is equipped with 2 grinding spindles. And that is, those grinding spindles are not in an angle, therefore the precondition for this setup is that the shoulders are turned in a pre-process. And now with those 2 grinding spindles, we can start to grind simultaneously our seats and the rotor diameter. And as you see, for the seats, we have a smaller grinding wheel that is capable to manufacture the downside seats and the upside seats by moving in Z direction. And we have a bigger grinding wheel to grind the complete rotor diameter at once. Of course, as I said on the example before, when you do grind such a seat with a transverse groove, we do have to get out of contact with the second grinding operation while we do finish grind one of those seats. But such a setup now can come down to a cycle time of 71 seconds, which would be 250 parts per year in the same tolerance classes as shown before. And now we did get another question I want to answer. How do you dress the grinding wheel and how often? That somehow depends if we use CBN or corundum, and if we do get into a combination process where the turning, where we have pre-turning, or if we grind the full stock. So normally we use dressing spindles for the dressing, but also dressing diamonds are possible, but they should not be used when we use CBN. And how often you dress, that depends on the stock and in the input quality that you give to us, and therefore that can't be answered right away. Just send us your process question, and we will answer that in detail there, I would say. But of course, if you use CBN, the dressing cycles are much longer than when you use corundum. Now let's go back to our processes. As you did see, we did get more productive with the examples. Now we will get even more productive. So we do have to get more simultaneous processes in our machine. And therefore, we do want to grind here the seats on the up and on the down side of the rotor shaft on the DS machine also simultaneously. And therefore, we need a wider grinding wheel here, which just cuts those seats in one plunge, while the rotor diameter is again cutted with the big grinding wheel on the second spindle. And also for the finish grinding processes here, those processes can't take place simultaneously. But now we get down with our cycle time to 54 seconds, which will be about 340,000 parts per year in the same tolerances than before. And now the question is how can we get even more productive? How can we get even more simultaneous machining? Therefore, we need to do the finish machining simultaneously, and to do so, we need to go on separate machines for this example here. And also, we do have to pre-turn our shoulders and to pre-turn all the diameters to get the stock down as low as possible and to get to the lowest cycle times. So here we have an example where we use at first a turning machine to turn the shoulders, the grooves, the diameters. And then we have two HG machines, for example, where we can grind in different manufacturing machines, but at the same time, therefore, on two different workpieces, the seats and the rotor diameter. Which such a setup we can get down to 36 seconds of cycle time, and therefore can get up to an annual volume of about 500,000 parts per year. So you did see, and I will show it here in the overview, that we have different solutions just depending on which amount of flexibility or productivity you do need on your machine, starting from a combination machine, going to the line set up with 3 different machines for as simultaneous as possible machining of the parameters. And regarding this slide, we do have another question that fits here very well. The question is, are the shown examples already realized? I can say you all those examples are real life examples. And therefore, we do have, as shown on the slide, for your real life problems, the solutions with different degrees of flexibility and productivity. So after this part about the e-rotor shafts, we now want to come to a part that is more general within our car. And Manfred, you will now just show us about the CV joint.
Yes, so I think this CV joint is an example. This part is used in each car. You need it. It doesn't matter if it's driven via a combustion engine, via hybrid, or via a battery. So first, let's have a look where this CV joint is placed. Here you can see on this slide, on the right side, the wheel side, and on the left side, we have the differential housing side. And between these two units, we find two CV joints which are driven via the drive shaft. Let's have a look more detailed here inside. This CV joint, you have outside a joint housing. This is the part which we will show you later some examples, how to grind these parts. Inside you find the inner raceway, you find the ball gauge, and you find the balls inside. And therefore, between the wheel side and differential housing side, always you find on the right and left side this joint housing, and it's connected with a drive shaft in the inner raceway. So now let's have a look to the first example. This is machining on our VTC 100 GT. We have to turn the groove, and we have to grind two diameters and the face, and one diameter must be twist free. Let's have a look on this icon on the right side. Before we had the question how we dress this grinding wheel. The dressing unit basically is placed here on the right side of the tailstock. And this is a spindle, and we dress this wheel with a rotating dressing disc. So let's come back to the process. Yes, here you can see the tailstock, and on the right side here, the dressing spindle is placed. Let's have a look to the process. What we have on the left side, the turning turret is used for loading, unloading. And also on this turning turret, we have the turning tools, we have the diameter measuring head, and we have also this position measuring head. On the right side, we have the grinding spindle with a wheel set for grinding these two diameters and the chamfer. We are using here vitrified bonded CBN grinding wheels diameter 400. And for this process, we are using emulsion for coolant. The cycle time is 36 seconds, including loading, unloading. And with this cycle time and shift model of the customer, we come up to 500,000 parts per year. So now I will show you a video for this process. This is the VTC 100 GT. Here you see the unloading of the finished part already on the pallet, and the gripper pick up now the new raw part, bring it in the clamping position. Also on the top side you see the dressing spindle. Then we have measuring about the axle position, and we have now simultaneously grinding of the diameters and turning of this groove. After the grinding is finished, we make a measuring of the diameter to check the quality, and then the gripper of the turret make the unloading of the part. The second application which I want to show you for the CV joint, it's a horizontal solution on our HG208 double wheel machine. This part now you see is much longer The length is 370 millimeter. We are using now 2 cross-slide on the machine and 2 wheels. And you see, we are grinding basically 2 diameters at the same time. This reduces cycle time. But here on this example, we have a second straight plunge on the right side because we have 2 different diameters. One diameter is also we have to make twist free. You will ask why we don't use a wheel set on this right side, because basically we can grind both diameters with one wheel. But our customer for this application, he has many different types, and the difference of the diameter is always different. And he don't like to change always the grinding wheel on the right side for each different part. And therefore, we are using the process on the right side to make this 2 diameter with the 2 plunges. The cycle time is less than 40 seconds. And the annual volume which we can reach is 450,000 parts. At the end, the concentricity request to the centers, what we have to reach is 50 microns. So these are 2 interesting applications. One our vertical machine with combination technology, and one on our horizontal machine with a grinding application. The last workpiece which we want to show you some applications today is the CVT shaft. And Tobias, now please give us more details.
Yes, the CVT shaft. At first, again, the question, why the CVT shaft a part of transmission in this webinar where we want to focus on our workpieces for drivetrain components. Now, the CVT shaft is, as you can see, an element in our transmission that can give you just continuous variable transmission ratios. And how this works, I will explain here on this example. In the middle, the golden unit is the CVT unit here. It is composed out of a CVT shaft and a CVT pulley that can be moved along the shaft. And both the shaft and the pulley have control faces with an angle, and those faces force the chain or belt in between them to drive on a different diameter. And this unit we do have 2 times in here, one on the front, one more on the back side. And due to the different axial positioning of the pulley to the CVT shaft, within both of those units we can get those different transmission ratios. On the right side of the slide, you do see those 2 parts, the pulley and the shaft, together outside of the transmission. And you do see that the pulley is just slipped on the shaft and can there actually be moved. How do we do that in future drivetrains? One example where it is used is the hybrid transmission. So those possible transmission modes together with the CVT can be seen in the left side of the slide. At first, we will begin with the parallel mode, where our combustion engine is put via a clutch on the same axle than our electric motor, shown in blue here. And then there is the CVT that can then adjust just to the correct transmission ratio for those combined engines on one drivetrain. The second mode is the electric mode. There the combustion engine does not work for the propulsion of our vehicle. It's just the electrical engine. And now the CVT transmission can just focus on this electric motor. The same can be done for the combustion mode. Here the electric engine does not go for the propulsion. It's just the combustion engine, and therefore here again now the CVT can focus on this combustion engine. Also, when the CVT is not used, we can just charge our battery using the electric motor as a generator, and use here for the combustion engine. And so you see here the CVT is for this hybrid transmission, a commonly used solution. Now I see here the next question. The question is the CVT transmission only for hybrid cars of interest? Well, I would say no. I have just seen the article of a big automotive supplier who proposes also those CVT transmissions for pure electric cars in order to enhance the overall car efficiency. And therefore, I do think that we will also see these CVT transmissions in the electric cars and not only in the hybrid cars. But now let's focus on the CVT shaft. We have seen the, I have explained the function of the CVT itself. We have seen the shaft together with the pulley or with the control wheel. And now what features do we need on the shaft in order to realize those functions? At first, on the right side of the slide, we see again a bearing seat with certain IT grades and RZ values for the roughness, and also with a running tolerance to the second bearing seat. Also to this bearing seat, again, there is a shoulder for the bearing to be pushed against. And then the next element is a CVT special element. It's a ball track groove that can be on such a shaft. It is used to limit the rotary movement for one of the pulley that is put on this shaft, and second, it is used for for an axial alignment of the shaft and the pulley itself, and therefore the ball track groove, as you see on the right side of the slide, does have not only requirements to its roughness, but also to the parallelism of the axis to the axis of the two bearing seats. Now after the ball track groove, there comes the running surface for our control wheel or the pulley, and this has again a tolerance grade about IT6, roughness about RZ4, in order that the pulley, when shifted here, actually can be shifted smoothly. And again, we do have a running tolerance of this shaft to our two bearing seats. Then we come to the control surface, where the chain runs up and down according to the axial positioning of our control wheel. And to ensure this running up and down to be smooth, there we do have a certain roughness required, which could be around 1.3 and 1 to 3 microns RZ. And of course, again, a running tolerance to our bearing seat axis. After that, the second bearing seat comes, which has again an RZ4 and a running tolerance to the axis of the two bearing seats. After this, the shaft for the transmission is ended with an input or output gear, just depending on which position in the transmission this shaft is positioned. This output element or input element can be geared, it can be internally, it can be externally, and also it can be designed that just the gear is slipped on there, like in the rotor shaft. That is up to the designer how he wants to design his here CVT. Now, how can we ensure those features? And especially, as you do see in this slide, the tolerances that are all set to the same axis of the two bearing seats. Well, such a toleration normally induces that you have to manufacture those features in one clamping. And that is what you can see here on an HG208 machine, for example. And that is equipped with 4 different grinding units that are actuated by an B-axis. At first here, we do grind the ball track. And in order to grind this ball track, we have to position our shaft correctly, that we do hit the ball track and just in the correct position. After this grinding, we come to the grinding of our control surface. Here we do face one problem. We do have to ensure special sizes of the control surface to other features on this CVT shaft, but we can't measure in process on such an angular surface really good. Therefore, we also do pre-grind our shaft on the bearing track here for the pulley. So, and now we can go just with a regular in-process measuring head on this shaft, measure the size here, and therefore know what size our control surface has. After the grinding of the control surface, we come to a plunge grinding of the long shaft together with the seat. This is our widest grinding wheel in this example here. And as you do see, we regrind the area we did use for the size measurement of our second grinding operation. And therefore we ensure that in the end, we do have one surface without any grooves or anything. So this grinding operation does give the final quality to the length of this shaft here. The fourth grinding operation now poses another challenge, because we do clamp on this side that the bearing seat is on. We are very limited in space here, but we do have to grind this bearing seat. And for the grinding operation 3, due to the wider grinding wheel, we did not clamp only with a face driver, but we really did clamp our shaft so that we do have a smooth grinding process here. But we can't do that for the fourth grinding process, since here we don't have the space and we need to go along our clamping arbor. And therefore here we did install a clamping arbor that can be retracted. And so for this small bearing seat, we can go only with the face driver and ensure here the quality of the bearing seat by this operation. So you've seen we have 4 grinding operations on one machine with 1 B-axis, done here with 3 vitrified CBN wheels, 1 electroplated CBN wheel. This is done in about 150 seconds cycle time, and that is about then 120,000 parts per year. And we do think 4 operations on one machine, that is quite a very interesting solution for such a shaft. And I also want to show you this solution in a video. You do see here the inside of our machine with the clamping, and also the workpiece is loaded. And first the clamping is put into position, then the positioning itself is done and ensured. The final clamping is done with the retractable clamping arbor. The position of the ball track is searched and then fine-tuned with measurement equipment, so that for our first rough grinding cut, here we do hit the right position of our ball track. And after rough grinding, we have to get to the final quality, and therefore here we do use a finish grinding operation, so that we do hit the right roughness values and ensure the quality. After the grinding of this ball track, there comes the grinding of the control surface. And as you will now see in detail, it is done with in-process measurement on the shaft to ensure the sizes here. And after the grinding of the control surface, now the wide grinding wheel comes into contact. And as you will see now, it will finish grind the whole length of the shaft. And again, here we do use in-process measurement technology, and we do grind the seat and the shaft in one go with one grinding wheel here. After this, we come to the area where it is a more closed shave. As you did see, we already retract here the clamping arbor, and now the smaller grinding wheel comes into contact, and you see it's already a close fit in here, but it works very well. And with our in-process measurement, we ensure also on this seat the quality. As I said, I think this is a very interesting example, not only because that we did use 4 grinding wheels on one machine here. But this example out of the automotive world leads to the next question I get shown here on my monitor. The question is, in your presentation, you did only show automotive parts. Does EMAG also machine parts for other industries? Manfred, technical sales, I think this is your question.
Yes, of course. We machine also parts for other industries. Some examples are for shafts for compressors or shafts for wind turbines. We also grind control shafts for printing machines, for textile machines, for packaging machines. We do also many parts for the hydraulic industry, for example, camering for a radial piston pump. And also we are grinding, for example, ceramic bearings, which are used in medical industry. So you see, in many different industries, EMAG is there at home, and we bring in our grinding solutions.
Very interesting, and I think the next question is also interesting, and it is, are you present at the EMO, Manfred?
Sure. We will join the EMO this year in Milano, and we invite all of you to visit our booth. Come to our booth in hall number 4, and you will find also there a horizontal grinding machine, but this time not for a production machine, this time for a universal grinder. So welcome to the EMO beginning of October in Milano.
So, and now for everybody, I hope that we will meet you in Milano and can show you our grinding technology, but not only that, but all technology of the EMAG Group. But if you don't have time to get to Milano, or you do have questions to us beforehand, I will show you some contact dates. You can either contact my colleague Manfred Winkler using mawinkler@emag.com, or you can contact me using trötlingshöfer@emag.com, and we will try to get the solution to your interesting work pieces. So now I can only say thank you very much for your attention. I hope you did enjoy this webinar as we did here in the studio, and we will be happy to get your questions and your work pieces here to EMAG. Thank you very much.